Hi everyone, I am Liyang. Today I excited to present the paper titled Boundary Privileged Knowledge Distillation for Semantic Segmentation at WACV 2024 conference. Now let's talk about the motivation of BPKD, Boundary Privileged Knowledge Distillation. Our presentation begins by posing a fundamental question. Despite the plethora of methods in knowledge distillation that have significantly improved the performance of student models, can we consider these student models to be sufficiently competent? We contend that the answer is negative. Our analysis reveals that even the most robust knowledge distillation techniques fail to adequately enhance the student model's performance, particularly in accurately predicting edge regions. This deficiency is clearly depicted in the section B of the figure provided. We hypothesize that this shortfall may be attributed to an issue of context information leakage. This phenomenon leads to increased levels of uncertainty, especially in spatially adjacent categories concerning edge pixels, and is more pronounced in student networks with lower capacity. Addressing this issue is, therefore, of paramount importance for the advancement of knowledge distillation in semantic segmentation. To illustrate this point, the figure displays uncertainty maps. These maps are generated by calculating the mean entropy from the first layer of the feature maps. We offer a visual comparison of our method against previous works, such as CWD, as well as against a baseline student model without distillation. In these images, the presence of brighter colors signifies higher certainty, or conversely, lower uncertainty. In this segment of our analysis, we delve deeper into the issue of contextual information leakage. To substantiate our observations, we have constructed an analysis comparing the mean entropy against the accuracy of pixel detection along edges. The plot presented here elucidates a discernible inverse relationship between the mean entropy and the pixel-level edge accuracy. Our hypothesis posits that when a model is engaged in learning textual features, particularly edges, it tends to integrate contextual information from adjacent categories. A significant insight from our research is the identification of a limitation in previous methodologies. These methods, which uniformly treat all regions during the process of distillation, are found to be particularly vulnerable to this issue. This leads to heightened uncertainty in the detection of low-level edge features, culminating in diminished accuracy at the pixel level along edges. To facilitate a comprehensive comprehension of our methodology, we introduce a novel approach termed BPKD. This method represents a departure from previous works in knowledge distillation and semantic segmentation, which predominantly employ a holistic view transfer approach. In contrast, BPKD adopts a decoupled distillation strategy, resulting in markedly superior outcomes. Our primary finding indicates that, subsequent to the application of our decoupled method, there is a notable improvement in both the edge and body regions of the segmented images. This underscores the efficacy of BPKD in enhancing the overall performance of the segmentation process. Our presentation delineates several pivotal contributions to the field. First, we have identified a significant limitation in existing knowledge distillation methodologies, specifically pertaining to the issue of contextual information leakage. This insight provides a critical understanding of the challenges in current practices. Secondly, we introduce an innovative knowledge distillation approach, distinctively designed to focus on the separate distillation of information related to the body and edges of objects. This method represents a novel direction in knowledge distillation techniques. Lastly, our proposed method has demonstrated exemplary performance, achieving state-of-the-art results across 3 widely recognized benchmark datasets. This achievement not only validates our approach, but also sets a new benchmark for future research in this area. In the realm of our study, the methodology is predicated on a bifurcated framework, encapsulating 2 pivotal components, the body loss, LB, and the edge loss, LE, as delineated in Formula 1. These components are the linchpins of our analytical model, each quantifying distinct aspects of the system under examination. To achieve an equilibrium in the contributory significance of these components, we employ 2 distinct weighting factors, LEB for the body loss and LE for the edge loss. These weighting factors are not merely coefficients, but are meticulously calibrated to harmonize the influence of each loss term. The equilibrium established by LEB and LE is critical, as it ensures that neither the body loss nor the edge loss disproportionately affects the overall outcome of the model. In this stage, I shall elucidate the primary architecture of BPKD, which is delineated from left to right in the visual schematic provided. Commencing with Section A, we observe that input images are processed concurrently through the teacher and student networks, culminating in the generation of final logits. Subsequently, we incorporate an edge detection module, which utilizes techniques of dilation and erosion to delineate precise boundaries for various classes. This module's edge mask is then applied to both the teachers' and students' logits to refine the learning process. Moving on to Section B, we concurrently compute the body and edge losses. The body loss quantifies the categorical similarities, thereby fostering the alignment of class-specific features, while the edge loss is meticulously designed to facilitate the transfer of boundary-specific regions. The intricacies of the edge loss component will be expounded upon in the forthcoming slides. Edge loss is articulated through two distinct submodules, the pre-mask filtering, PRM, and the post-mask filtering, POM. These components contribute to the refinement and enhancement of edge detection in image processing. The initial phase, pre-mask filtering, utilizes spatial-level Kullback-Leibler (KL) divergence loss on masked edge pixels. This approach is primarily designed to optimize the probability distribution, encompassing exclusively edge pixels. Consequently, this method significantly enhances edge regional classification. The underlying premise is to improve the model's ability to discern and categorize edge regions with higher accuracy. To elucidate, let us consider an example where a photo captures a dog adjacent to a cat. In this scenario, the logits activation is confined to the dog and cat classes, while other activations are disregarded. This targeted process allows the student model to concentrate more effectively on the intricate relationships between adjacent classes, which may otherwise be a source of confusion. Subsequently, the post-mask filtering stage involves duplicating and compressing the output derived from the prior stage. It then reapplies a normalized soft edge mask, which is instrumental in aggregating contextual information across adjacent categories. This process culminates in the generation of the final edge loss. In the POM phase, the edge loss for each class is segregated and normalized relative to the edge area. This involves considering the logits for the Seath class at pixel I in both teacher and student models, represented as ZIT and ZIS respectively. The process also utilizes a soft mask, MEC, derived from average pooling the binary edge mask for the Seath class, coupled with NC, denoting the count of non-zero pixels in MEC for that class. The POM term, as delineated in Formula 4, is pivotal in reweighting the loss based on the edge area of each class. This approach prioritizes the center of the edge, which typically harbors crucial information. It ensures that the student model precisely learns the correct edge positions and shapes pertinent to each class. We advocate that through this specialized edge loss approach, not only is the edge detection refined, but also the body region of objects gains heightened attention. This leads to a more nuanced and accurate refinement of the object's inner structure. The page before you exhibits the visualization results that corroborate the efficacy of our proposed methodology. Displayed on the left is a figure generated by class activation mapping, CM, which distinctly illustrates the superiority of our approach over prior works. The comparative analysis reveals that our methods enhance the delineation and accuracy in both the edge and body regions of the subjects under study. This advancement is evident in the precision of the edge detection and the fidelity of the body region segmentation, signifying a substantial improvement in our model's performance. In order to ascertain the efficacy of our proposed knowledge distillation methodology, we conducted a rigorous evaluation of the segmentation performance within edge regions, as delineated in Table 3. This assessment utilized the TriMap MIOU metric, implementing both channel-wise and pixel-wise normalization techniques within the network distillation process. Our findings indicate that channel-wise normalization precipitates a decrease in the standard MIOU by 2.16% and in TriMap MIOU by 3.58%, thus underscoring its heightened sensitivity to edge regions. In contrast, pixel-wise distillation augmented the TriMap MIOU by 6.03%, which can be attributed to the ingenuity of our specialized edge loss design, a design that markedly enhances boundary quality. Furthermore, the body loss function demonstrated an augmentation in the standard MIOU by 5.18% under channel-wise normalization and 3.71% under spatial-wise normalization, highlighting its pronounced efficacy in the segmentation of body regions. Nonetheless, its influence on TriMap's performance was observed to be marginal. In summation, our tailored approach, denoted as BPKD, yielded the most superior MIU scores at 75.94 plus 6.95% for the standard evaluation and 62.91 plus 7.59% for the TriMap evaluation. These scores are emblematic of the BPKD's robust capacity to refine semantic boundaries and body regions, leveraging pixel-level alignment and context aggregation for optimized segmentation performance. This table shows the performance comparison of different distillation methods with state-of-the-art techniques. We test these methods on various segmentation networks for both student and teacher models, using datasets including Cityscapes, AD20K, and Pascal context. The flops and FPS are obtained on 512x512 resolutions. Our BPKD outperforms all previous methods in large margins across multiple datasets and network architectures. Thanks for watching.